be a fish passage engineer. A little bit about Gabe. He has almost 20 years of combined experience in transportation, construction management, and hydraulics. His current focus and passion is implementing Washington's fish passage projects, and Gabe has worked on a wide range of hydraulics, from fish passage on the smallest size streams to large woody material revetments on large rivers in Washington. So as long as Michelle gives us the go-ahead, I think that's everything we need to have Gabe take over, and we can start our presentation. So thank you, Gabe.
Thanks, Caitlin. Thanks, everyone, for coming. I appreciate being here and being invited to this. I used to be actually past president from the ASCE North Seattle chapter a few years back, so it's nice to be back and get to be reconnected with some of the folks here. So yeah, today I'm going to share a little bit about how to be fish passage engineers. So from the folks I see on the call, many of you are that already, so you get a kind of taste of kind of from my perspective. So Caitlin did share a little bit about my past experience. I guess I'll share a little bit more personally about myself. So I live in Bellingham, Washington, with my wife and 5 kids, and been at Jacobs for a little over a year. Before that, I was at WashDOT for 5-6 years, and then before that, I was at a consulting firm, had my own business for a while, and before that, I was actually, when I first came out of college, I went to WashDOT out of college. So there's a little bit about my background, give some insight there. So I kind of struggled to see what I was going to present on when Caitlin asked me to present on this group. So I knew a lot of hydraulic folks. So I'm thinking, okay, well, with today's fish passage market, I thought I should see if I can try to encourage more hydraulic engineers to join the fish passage movement. So I haven't done this before. I could see if in this live setting, but I want to get a sense, to show of hands, how many people on this call would market themselves as a fish passage engineer? Is there, hopefully I can count these hands, or not hands, maybe thumbs up. You guys do like a thumbs up or something to see. Maybe I can't even see these. I can't even see them. All right, well, that didn't work. All right, well, forget about that scenario. I was trying to get a sense of like what the size of the group was here that's done the fish passage before. Anyways, all right, well, so I'll share my experience in this kind of presentation, kind of highlight a project that Jacobs worked on, sharing some basic design approaches, share a little bit of how implementation into construction, and hopefully I convinced you guys by the end of this to join this fish passage movement if you haven't already. So I'll start by telling you that fish passage engineers and that work has great stability, meaning that there is a ton of funding out there to support it. I'll also share with you why I think it's really the best bang for your buck. So if you're thinking restoration, it really has a high cost benefit ratio if you're really trying to focus on habitat for fish. One of the reasons I'm a fish passage engineer is I like to see that immediate results. Once the project is complete, you can go out to see the fish literally swimming upstream of your project, and you've essentially opened that door that was otherwise shut for fish to pass and utilize that existing stream habitat. The other part is just really that feel good of making a difference. Again, a reason why I connect with fish passage is I like to work in that fringe where the natural world and the developed world literally intersect. And as an engineer, trying to find that balance between both the human living environment and the aquatic environment, and trying to get that to thrive together. So fish passage really requires a multidisciplinary approach where the primary disciplines, in my experience, is not actually engineering. And after putting together this presentation, I joked with some colleagues about how much engineering is actually in fish passage is kind of funny, because it's really starting to get removed away from it. But the engineering is still important, and it provides those checks and balances. But like I said, if you're really doing it right, the leading disciplines are really your science-based geomorphology and biology. The The engineering is there for that human piece of it, understanding how the designs really interact with the infrastructure, and to make sure and to balance, to see what kind of risk to life, property, or structures would be. The reason fish passage is also exciting to me is there's no two fish passage projects are alike. You have to start each project by really understanding what the existing conditions are, and you really focus and study that. You need to read the land, and I'm going to hit this one really hard later on in the presentation. This is that geomorphology piece. So what's the purpose of all this? The fish, right? Too often I get in deep conversations with engineers or resource managers, and we actually lose sight of why we are here. We often have to remind myself or ask people in the room, like, hey, what would be best for the fish? Where's the fish biologist? Like, we're stuck between these two concepts, what type of habitat do we need to create in this location? And that'll start to go into some of the restoration pieces that I'll also talk about in this presentation. So like I shared, I think my, Caitlin shared or maybe she didn't, I don't know, my role, I guess current role is a design manager. So at Jacobs, I staff augment some of WashDOT's hydraulic staff, and some of the design manager for the fish passage projects at WashDOT, primarily in the Northwest region. So what I do is I provide a lot of the engineering checks and balances. Engineering is specific to what folks call the H&H. I think everyone here knows the hydrology, hydraulics, where we're looking at the developing hydraulic modeling. They're developing, which are looking at the water surface elevations, the water depths, velocity, shear stress. This is stuff that I think everybody on this call understands. But what that boils down to is we're trying to size the structures. And in the fish passage world, we call these the minimum hydraulic opening. So that minimum hydraulic opening is looking at that width and that height and the freeboard on the high side, and then that scour on the low side. So that's kind of what the engineering piece kind of wraps into. And then finally, I'll show and share some finished products. Kind of like these two pictures that you see on this is some final products, and to see how these types of projects are constructed in the field. Because to be honest, as engineers, we probably don't get out in the field as much as we want to. So I got some kind of time series videos that I'll share with you, as well as I have a few videos that will kind of show the fruits of our labor, or the fish of our labor in this case. So what are we spending on fish passage? This blows my mind in some regards. So WashDOT had a federal court order in 2013 found WashDOT and Washington State culverts that violate the 1855 Treaty of Point Elliott and the Bolt decision of 1974. And that guaranteed the tribes permanent access to their usual and custom fishing grounds. So under the court order, the state had to accelerate its pace of culvert work that was specific to threatened endangered species and salmon. So this is where you can see that the WashDOT has set aside $2.4 billion for fish passage, and that's just what they've allocated. The cost of it is closer to $4 billion. So that's a ton of money just in Washington State, and it's kind of dumped in mostly the Puget Sound area. Any of those water bodies, that's the injunction area that flows into the Puget Sound, is where a lot of that money is going. So this other funding package that just rolled out last month, if you're not aware of it, this came out from FHWA. This is part of their National Culvert Removal Replacement Aquatic Organism Passage. This is a $1 billion grant for 10 years. I think it's 10 years, 8 or 10 years, but for the next biennium, there's $200 million. And so this is a big package that just rolled out. So for those local agencies, the tribes, folks that people we're working with who say, we don't have any money, well, there's a ton of money that just kind of rolled out. So pointing folks to that. King County is another big entity. They have $20 million just to finish up their program this year. And they also have another $150 million for the next 10 years. So tons of money just in King County alone. And then there's the last one, and I kind of, DFW, Fish and Wildlife, they have their Fish Barrier Removal Board. Their grants budget for the next biennium is $85 million. And so there's a list of that online if you want to see which projects got money. So that's a big chunk of money out there. We created this problem, I guess, as humans. We degraded much of our stream, And so there's a lot of money now to we're realizing we did something wrong, and now we're up money's out there to restore it. So the cost of stream restoration is estimated around $1,200 per linear foot. So if you look at this is just stream restoration, not fish passage. So if you took that $1,200 per linear foot, for $1 million, that buys you just under 1,000 linear feet of restored stream channel. But for that same $1 million, you can correct a barrier based on some of the numbers that we've come up with, some cost estimates, and you can open up miles of stream to existing habitat. So I'm not saying I'm against stream restoration by any means. I'm just saying that humans do a great job of destroying that stream habitat, and we really suck at creating stream habitat, or restoration, I should say. So I just figure, like, I was just focused on creating these passage, correcting these barriers that we've created, and then let Mother Nature kind of be the restoration. So this slide, like, hopefully you're reading through it. I'm not going to go through it. This just really shares a lot of estimated costs of barrier replacements. Also, there's a lot of active washed out projects that have been recently awarded or are currently on advertisement for bid. So this kind of builds back on my claim about the project security, or the job security, I should say, for being for working in the fish passage market. All right, so fish passage projects, they provide immediate results. Go on. This is a video that I took of sockeye salmon returning to spawn in Lewis Creek, just up from Lake Sammamish, but they've reached the end of the road. This culvert's inlets on the right is 1,000-foot long, 4.5% slope. This limits their access to those spawning grounds, which is this. This is a photo of the upstream. This is untouched natural habitat that we don't need to work on restoring it, or it already exists. We just need to get them to where they need to go. There's a quote from a local representative last month that talked about the salmon. It said, salmon travel hundreds of miles to spawn only to be blocked by barriers within a few miles of pristine habitat. Simply put, culverts are wiping out salmon on the 1 yard line. This is the Marshawn Lynch Super Bowl, where there's a touchdown on the right or the end zone on the right, and they just can't get there. So that's sorry, bad joke. All right, well, making a difference. So most of the stream engineers I work with have the same inherent desire in common. We all want to be better engineers than our forefathers and better balance that built environment with the natural environment. We get to do that through our work in fish passage and stream restoration. And I remember saying to myself, I can't wait to show my kids the fish barriers that I've helped correct in my career, and then take them to the streams to see the salmon run. Well, I'm old enough to say that I'm there, and these are photos of my kids, some of them, and we're out there, looking at the streams, finding fish. So whether you have kids or not, this is actually a great time to start getting out in the streams. It's been dry for a while, so probably not much moving right now, but after we start getting a few more rains here coming up, start to see fish kind of running up these streams and tributaries. So take the time, take out friends, family, significant others, and get out and see these fish in the streams, and maybe you can pick out a few barriers while you're out there. So this is making that difference part. All right, so here's where I step into the process of designing a fish passage project. So there's the desktop analysis. Before you're going out to the site, you're pulling out maps, you're looking at the geology, you're looking at LiDAR maps, land use. You might do some coarse hydrology to get a sense of what's coming down the pipe. You're looking upstream, downstream, other barriers that may be on site that may impact the crossing you're working on. The DFW has a great website with all these barriers listed where you can actually switch over to different maps to get that 30,000-foot view. And I tend to actually use the hillshade map just to kind of read the land, and then turn on the hydrography and the topography and fish distribution. So this is a good first cut to see what's going on out there. In this example, actually, you can see that the stream is really confined in that upper reach. And then as it reaches the highway, which is the red line down at the bottom, and then there's kind of a blow up there, you can see this historical alluvial fan that's been depositing sediment over the years, where the stream's really mobilized out of all that sediment from the earth. And this is Log Boom Park in Kenmore, for those who may know the area. The sad reality is that alluvial fan is completely developed and has $1 million condos sitting on top of it, with people who usually complain about sediment and flooding. So that's a sidebar. Anyways, let's jump into another project example. So this is one that Jacobs has done. This is a design that's been complete. It hasn't been constructed yet, but this is a project north of Stanwood on I-5. This is just north of the scales. There's some scales on northbound. So you got flow coming in from right to left. It crosses the frontage road, Hall Road, that's the county road, crosses I-5 northbound, goes into a median that's vegetated, and then crosses southbound I-5 before it goes into kind of a wetland reed canary grass section. So as I mentioned, the first step of any fish passage project is to read the land, which is really actually the part I enjoy the most in the design phase. So we're really assessing the site. This is usually led by a fluvial geomorphologist. And for those who don't know, that is a licensed geologist who has a focus in fluvial processes, which is specific to that interaction of water and sediment over the land. So in addition to that geomorphologist, you need a solid stream team. And so it's geomorph, you have a biologist, hydrologist, and a hydraulic engineer. So these disciplines are really critical in covering all those areas necessary in fish passage project. And in this map, you can see the stream team with these people there identify those different types of reaches in the system, including reference reaches, pebble counts, bankful widths. As we continue to read that land, an important piece to the puzzle is this overall stream profile. And that's what you're seeing on the right, and try to see what land features are modifying its natural path. So in this case, we see the road embankments or the culverts crossings that are really impacting that prevailing gradient, starting from that upstream slope of about 4+%, and then it flattens out down to a 1% of the crossing. Now, it doesn't seem like much transitioning from that 4% to 1%, but as I'll show you, water moves very differently down slope with even a 1% change in slope, and I'll share that later on the last slide for this section. But the point of this is to really make sure you take in all the story being told by the land before you start into your design, because there's a lot of answers that are just right in front of you, but you just have to make sure you're paying attention and leaning into it. Here's a few of those photos that you're in the field. This captures kind of those reaches that were identified in the previous slides. On the downstream, you see a confined reach. So this channel has responded to kind of probably disturbance, and this has reestablished a new floodplain. It has it's lower in elevation. It's kind of in size, but the channel hasn't quite widened yet by any sort of bank failure. So that just you get that by just standing around a lot of geomorphs, I guess is the best way to say it. On the right side, you have an unconfined reach. You have a braided reach. This may represent a kind of a pre-disturbance. It's kind of an anti-branching network, as we call it. And then it transitions into a single thread channel, but it currently exhibits multiple threads and extensive sediment deposition. And this will come back around here in another slide. So reading the land, here's the field notes and the map that the stream team has taken. Probably some folks on this call is probably their chicken scratch that they're reading. Half of the team probably didn't know I was presenting on this, but anyways, they're looking at reading the land while their feet are literally in the stream. And so this is what they're looking for, is the stream morphology. They'll touch on it in a minute. Channel geometry, I'll touch on that one next slide. Flow regimes, that's the different types of flow rates that you're expecting to come through your system. Sediment, you're doing pebble counts, you're trying to get assessment of what type of mobility is occurring or lack thereof mobility. Maybe you're dealing with big boulders. Substrate or subsurface, I guess, that's where you're kind of maybe taking grab samples and getting a sense of what's going on underneath that armor layer. Looking at constrictions up and downstream that may occur, stream features like large woody material or trees or jams, and that kind of rolls into the habitat, which is also made up of vegetation and, like I said, any other constraints that you might see due to any development. So this is a big part of doing some of that field work and getting out in the field, is measuring the bank full width. And so bank full width has historically been kind of the driver in how to size your structures. So in this case, there was multiple 6 feet, 7 foot, 6 foot, and 7 foot, so 6.5. So we're averaging 6.5 feet of bank full width. So that kind of gives generally a sense of what the channel wants to become in its natural environment. And one thing that I tell teams, which is hard to do, is try to, as you see these in the field, imagine what that 2-year flow looks like. Where's the water going? What does the 50-year look like? What does the 100-year look like? And those are as the engineer, those are what you want to look for. You want to look at those design flow rates, which are pretty rare, but you still want to understand what's going on at that 100-year. That goes into the engineering stuff that I'll touch here in a second. Okay, so the last slide I want to talk about was this the stream morphology. So this is adapted from Montgomery and Buffington in 1997. So these are typical morphologies, stream morphologies in the lowlands of the Pacific Northwest that we're used to seeing. The steeper reaches when we get up into the mountains, or more of a cascade, which is greater than 7%. And then in the flat, if you get down to the flatter areas, we're kind of talking wetlandy type streams, which are less than 0.5%, and those are typical Western Washington. So the difference between what you're seeing on the left and the right, so the one on the left doesn't show the wood presence. And so the example on the right is what we typically are seeing, and what we built in an example project is kind of that wood forest step pool morphology. And so you can almost apply wood to any 3 of those: step, pool, plain bed, and pool riffle in any of those slope gradients, and you're going to get a little more dynamic stream morphology. And so that's the important piece to fish. And so I'm going to hit on that, but remember that the diversity, the complexity, the variability, that's the key to that. Here we are. So this is what I asked one of my fish friends this, like, so how do we design for fish habitat? And he really told me really plainly, says, just look around you. If you can match the natural conditions that Mother Nature has done, well, then the habitat will just take care of itself. So this sounds a lot of like what we just did, matching the reference reach. And so this goes back to, again, reading that land and seeing what the land is doing, where the complexity is occurring. So fish passage is not just fish passage anymore. We can't just be engineers and look at making sure we're conveying from one side to the other of a crossing. We have to start to think and consider the restoration aspects of this. And WashDOT has actually done this by they've retitled, or they're shifting their training. Their fish passage training is now called fish passage and stream restoration. So some of you folks are signed up for that in December, but it's not just fish passage, it's and stream restoration. So most often the work done in the fish passage world requires that additional stream reconstruction up and downstream of a crossing. So we're already there replacing and removing. So providing some additional restoration is typically pretty simple, and it's not a huge lift compared to the structure that you're replacing. So we're just trying to create that enhancement of that crossing, so when the fish are able to move, they actually have something valuable. And a lot of times, since the right-of-way is already owned by, most of my situations are WashDOT, it's like, well, we own the property, let's just do the right thing and be stewards and put some quality restoration, up and downstream of our crossing. So the other benefits of habitat is the sediments. The riparian vegetation, those stream features, in-stream complexity, which could be wood or plantings, as they're saying. So this diversity is what fish habitat is the variability of flow velocities, the variability of depths of pool, variability of sediment sizing. I asked another fish friend of mine, like, how do I know where the fish are? What's the fish habitat? I said, well, if you were to go fishing, where would you throw your line? Now, of course, I'd throw it underneath these pools or around the riffles. I mean, that's where the fish are. So it's not rocket science. It's just trying to create that variability is what we're focusing on. Here's an example of kind of an intense restoration effort. This is done on SR20, tributary to Skagit River. So the downstream of the arrow is the Skagit River. So we had opportunity to kind of go high risk here and just throw a bunch of wood at it. So when we add wood to these systems, we're creating that variability. We're creating some obstructions, which are going to create some changes in velocity, create scour, which creates depths of pools, which helps to sort out sediment. And so we're getting that variability through this type of concept design. So that's pretty cool when we can get outside of our crossing. This is actually flowing right now. This is an old photo. So I haven't been up there since that culvert's been installed and water is moving through it. So this is, again, it's a good time to go up there, maybe after a high flow event, as Skagit rises, and see if fish are up here in this tributary. So that's great when we're outside of a crossing, but what about inside the crossing? How do we deal with that? So I got to give credit to Channing Sims. He's one of my co-leads on the design realm, design managers at WashDOT. He put together this rendering and a lot of the design work on this. Also, so kudos out to Derek Marks. He's also was a big part of putting together this design concept. But this is, in this concept, these are meander bars. We're looking to mimic those natural conditions that we would see outside. This is that advancement of the biomimicry and the eco-hydraulics, as we're calling it. We're trying to create that inside an unnatural place. So the evolution of these designs has been challenging, but we're really trying to find the tools that help us to mimic those natural conditions. This in itself is creating a hard bank. It's not part of the bed, but it's a bank feature, hard bank feature that's dissipating energy and creating a scour hole. And so again, we're creating some diversity in the stream, in the hydraulics, where we get increased velocities, increased shear strength, and then we get pool formation. And then you get tail outs on the backside, so you get some slow moving water for fish to also hang out in at higher flows. So this is a great example that we're using more and more often. We just don't have the opportunity to put in, trees can't grow inside culverts, and we don't always have the room to put in large pieces of wood. So that's what these are really emulating, is these large bank features. All right, so this is jumping in a little bit to the design side of things, the engineering as I call it, but we'll see if we actually touch the engineering. I did learn early on from one of my mentors in the fish passage world that in designing a fish passage, that there are many different ways to design a successful fish passage project. You just want to make sure you don't choose the wrong one. And what this means is, it kind of goes back to my duties as the design manager who reviews many of these fish passage designs, is I don't always dive into the details and telling people how to do it right or tell them how to design it. I just make sure I'm asking the right questions to make sure they're not going in wrong directions. Or if I see a risk to a project, I say, well, how are you going to address this, or how are you going to mitigate that? So there's many ways to get a successful project, but there are some known pitfalls that we try to avoid. And so that's kind of becomes my job, is trying to identify those higher risks elements, particularly to life, property, or infrastructure. So the engineering, as we're going to call it, begins with how much water are we dealing with? What's the estimated hydrology? I don't know if anyone calculates hydrology. I think we really estimate it. So I'm not sure if we can call that engineering quite yet. So in this example, there's two different methods that were looked at, and ideally the design team will justify which method that they chose over the other. In this example, they were pretty close. So if anything, this just assures you that the hydrology that we're starting off with is probably pretty accurate. All right, so next steps in the engineering world is to run these existing conditions. So many designers I see actually rush through this existing conditions model so they can really move into their proposed design. And I say, hey, you know what, sit in that existing conditions and really understand what's going on in that conditions, what's happening in your model in those reference reaches that you were able to hopefully model. You're not always able to model reference reach, but if you do, what's going on? Remember, that reach is what we want to match or mimic. So if we can use that to see what's going on, then that's going to help us understand the stream bed material sizing, the bank composition, how different flow regimes will move through that reach. And essentially, it'll help us to identify what type of fish habitat is present. So after that was the mesh photos I showed you, but the next, you start to develop you turn your hose on, you turn the hydrology on through your system to see what flows are looking like, what are depths looking like. This is the SMS SRH 2D developed by Aquaveo for those who aren't familiar with it, but flow is coming from right to left, by the way. And so you can see on the left in the existing conditions, there's a backwater at the roadway condition. This is on this. I switched on the southbound. I don't know if folks followed that, but like I said, this Freedom Creek crossing, there's two crossings. This is a southbound crossing, and you got a backwater condition occurring on the upstream in the existing conditions. And the proposed conditions that's allowed to flow, you get more diversity in stream velocities and depths, as well as sediment diversity. So this goes again back to enhancing or increasing some of that fish habitat. So if you back up, I wanted to throw this slide in last minute, but I didn't get to it. But if you back up and reread this land, you'll learn that this area is part of a drumlin geology, which is described as kind of a rolling hill formation formed by the glacial ice acting on underlying unconsolidated till in this area. So you kind of try to understand, what does this look like before the road existed, and this is your proposed conditions or your future conditions is what it used to be. And so, because originally I was looking at this like, oh man, we're flooding out this area, but if you go back and look at that drumlin geology, that's what was created, is all these little wetlands in between these kind of rolling hills. So it just goes to support, what you're reading, and it kind of closes the loop on that. So now I'm jumping back up to the upstream crossing. Maybe people aren't even following that, but that's fine. This is just an example that shows kind of the comparison between the existing and proposed. And you can see, again, the backwatering in this case is set up behind Hall Road in the existing condition, causing sediment deposition. And that's that braided interbranching unconfined reach that I showed you a picture of. So that's occurring up there in that upstream of Hall Road. Downstream, the condition is showing a localized rise, but this it eventually returns to its equilibrium water surface elevation a few hundred feet downstream because of continuity of fluids. So you'd be surprised actually how many people I had to explain this. We tell them, hey, we're replacing this crossing, and they live on the downstream or something, or someone's concerned. They say, well, once you remove that, you're going to be adding more water into through the crossing. They're like, we're not adding more water. It's the same water. It's just we're moving the impediment or the constriction. So just basic continuity of fluids. So okay, so here we are. This is where the engineering actually comes in, or well, not really, or not anymore. Maybe it used to. Well, here, let me just explain this. So engineering is actually kind of starting to be phased out, because a stream really shouldn't have anything to do with engineering, except that maybe I touched on maybe the scour calculations, or I don't know, someone could probably think of something else that's engineering. But anyways, the stream simulation equation that some of you may be aware of, it calculated the width of a crossing that was to simulate a stream. So this was that equation, bank full width, that we measured on the field, times 1.2, which is essentially just 20% more than the bank full width, plus a fluff factor of 2 feet. So that was the engineering, if you want to call it that. But nowadays, that's truly just the absolute minimum that we're starting with. That's kind of the starting point. Because in today's fish passage world, we're really looking at that continuity of channel processes. So for those who are familiar with the hydraulics manual, it's good to read that every 6 months. I tend to read that every 6 months because I need to remind myself, what are we looking for? So that continuity channel processes is kind of a reach-based approach to allow that continuity of those processes, such as the natural movement of water, sediment, wood, and aquatic organisms can occur. This requires investigating the system as a whole, rather than only focusing on that channel corridor near the roadway. So as part of the system evaluation, defining an appropriately sized channel corridor within a water crossing is essential for sustaining that natural stream function. A variety of techniques and tools have been utilized to assess that continuity of natural process. You can see kind of the list that I just kind of started building this based upon reviews and consider this, consider that. A lot of them go back to kind of lateral migration, velocity ratios. I mean, there's some checks and balances, but if you start to look at them individually, you start to realize they all kind of come back to kind of just that continuity of channel processes. This kind of helps there, I guess. The bottom line is allowing that continuity of channel processes supports that sustainable, resilient, and reliable transportation network that we're trying to put together for the traveling public. All right, so you have your stream morphology that you're mimicking. You got your stream material you're mimicking. You have your stream geometry you're mimicking, stream features you're mimicking, and you get this final stream plan. But you still need to get restoration elements. So those are the in-stream features, I guess. This is the large woody materials. This is the bigger piece. This one's edgy a little bit. We put a longitudinal log. For those who know, we put a Martin log in the structure. Hasn't been built yet, but we have enough space to do this. This is not even in Martin's UNA, but we're going to give it a shot here and see if we can't make this work. So the next phase after this is really just package this all up using other civil elements to help support a bid package, and then put this out in the streets for bid and into construction. So this is the fun part. This is not a whole lot here, and I'd be happy to go into construction and conversation and questions if people have them, but this is kind of the work part. This is getting to see things finally get built. So this is a time-lapse installation of wood downstream of landing strip. I shared a couple photos of this one already. One takeaway from this one, if I were to do it again, would be something I learned this past year is about the incorporation of slash, which is just small woody debris be incorporated into, as we're backfilling this, I would incorporate slash back into it all the way up to the high water mark. That helps with stability in the log, and so prevents some of that incising that actually occurred on the site. So that's a huge takeaway. And actually the wood and the logs helped maintain the stream bed that could have been otherwise been worse off if we hadn't put it in there. Here's another time lapse. This is Logan Creek in Mount Vernon. This is actually inside the channel. This view is looking upstream, like this is literally in the stream channel. And you can just see the amount of wood that's being incorporated into the stream channel to support the habitat piece of it. This was probably by far the most intense wood layout that I've been a part of. It was the density. It was the density that was intense. Here's another solid project. This is in Concrete, Washington. That's our 20 Lorenzen Creek. This one you'll start to see once the camera moves is the meander bars installed in the structure. We actually added a meander bar, so if you watch closely, you'll see a meander bar gets added later on the upstream. But this is a good example. It shows that sinuosity, shows how the meander bars are functioning, and the wood also are supporting that habitat function. Sad piece of this, and the idea is the sad piece of this is there's an upstream culvert. You can see it through the new culvert. That's a barrier to fish. So that's the piece that hopefully with this project it gets that project funding and gives them a reason to replace that and then restore future habitat upstream. So, all right, so this image, this imagery, this video goes back to showcasing those immediate results and making an impact. So this is a steelhead. This is a video I was able to take upstream of a crossing that was repaired or corrected last year. So this is up in Padden Creek, up in Bellingham. And so there was a mate that this one was with, and it was just cool to see a steelhead that close, just hanging out there. Here's another pair of coho I noticed under a newly constructed bridge. This is up on Taws Creek. There's actually a pair of coho spawning underneath the bridge here. These are those field days I go out and take the kids on the weekend and we see it. So these are those rewarding videos that I enjoy sharing, enjoy talking about. This is the reason I really got into fish passage engineering, and a good reason why many of us should give it a try. I think salmon are known as that keystone species, as they are a sign of a healthy ecosystem. They contribute as a food source to humans, are particularly more valuable to the indigenous cultures because of their spiritual and cultural values. Food source, larger mammals and species, and they're also a benefit to when they decay, the nitrogen and the phosphorus that they contribute to the systems is invaluable to the plants around them. So with that, I'll take questions either in the chat. I think I might have to can't see anything here, so I'm wondering if I'm still even presenting.
Gabe, if you want to keep presenting so that if people have questions on your presentation, I can read you those questions. It looks like Perfect. We have one hand raised. If you would like to ask your question, Charles.
Hi, thank you. Hello, everyone. My name is Charles. I work for Kimley Horn and Associates Consulting, newer firm to the Pacific Northwest, and I'm intrigued with stream restoration. And so I just had a question. Has there been some or a lot of emphasis on making sure you aren't importing materials that aren't local to the site? Has that been achievable in most projects, or was it really hard to source all the materials needed for the restoration locally?
That hasn't been too much of a problem recently. I've been part of a lot of the materials sourcing. I've been out to the gravel pits. I've been out to some of the sites where they needed inspection on large woody material. I do sense that there's an increase in uptick clearly with restoration elements. And I know projects that are, utilizing thousands of pieces of wood. And so I think there is a need clearly of trees and wood. And I've even heard the flip side of the potential deforestation or the destruction of natural areas to restore other natural areas. So you're kind of trading one forested environment to a aquatic environment, and is that really something we should be doing? And so I know there's some debate on that. But material wise, it hasn't been an issue, but it's definitely a concern moving forward.
Nice, thank you.
Can see now. So
any other questions immediately? Bill, would you like to ask your question?
Sure. Hi, Gabe. Well done there today.
Thanks, Bill.
I'm at Radicke Associates, and we're natural resource consultants doing assessment of existing conditions for site development in various forms. And what we go through is assessing what the existing critical areas are there, and then permitting for those, whether it's for restoration or a site development. What's the permitting process? What's inherent in this? Is there a route that's been established to help with these sites, or is it pretty traditional in going through the Army Corps of Engineers and WDFW hydraulic project approval and those kinds of permitting? What's involved in these projects?
It is. It's they do offer some streamlining for fish passage because it's a restoration project and not necessarily a development project. So there is some streamlining that occurs. They tend to clearly look more favorable in these realms. I know that so that answers your question on the fish and wildlife in the Corps. One challenge that recently impacts us all is there was a rescindment from FEMA on the flooding aspects of crossings because there was a hydraulic impact, and I don't know the full storyline, but there used to be a streamlined FEMA process that allowed streamlining of fish passage project. That's been rescinded, and so that has been a huge lift or huge cost to a lot of fish passage projects, and we almost reverted backwards to that challenge of having to deal with that. So if you have a fish passage project within a FEMA or a hazard zone, then you're going to have more time, more costs associated with it to justify either a no rise or some sort of CLOMAR, LOMAR process that's now implemented. So yeah, there is opportunity to streamline on some regards, but and most people are familiar with that. If you reach out to those resource managers, they have that process kind of dialed in. But the one that we are just getting our heads wrapped around is the FEMA stuff, and so that one's pushing projects back a year, just dealing with things that might have no real effect on anything. So anyways, I kind of sidebarred that.
And just as a quick follow on, I imagine that wetland and riparian zone restoration designers are commonly a part of your team. It seems like once you get into the stream channel and start affecting wetlands and riparian buffer areas, that in the permitting, there's an expectation of some degree of replacement, either in place, in kind, or off-site, out of kind. Does that get involved in your projects?
You know, that is not as prevalent. I think there's a inherent, and I'm not a permit specialist, but if I recall, there's kind of an inherent self-mitigation. Like it's the site itself is self-mitigating. So if there is impacts to critical areas, which there is, clearly you're in a stream, that the inherent return is going to be a betterment than the impact itself. So I don't think I've been on those other projects where we're counting square feet, and counting square yards of material, and we're, and in this case, I know it's still being done, but it's not, the detail's not necessarily there. The scrutiny is not nearly there, but maybe someone else can respond with that who has better knowledge in the chat. But it's definitely permit. I've kind of tried to remove myself from the permitting side because I never always could remember or understand the why. My engineering head, I guess.
Yeah, usually in most projects, there'd be some kind of trade-off of recognized square, as you were saying, square footage of area impacted with the recognized replacement in the same place of square footage, or buffer enhancement, that kind of thing. Very good, thank you.
All right, thanks, Bill. Bill Cohen, an old friend. I see your hands up. You got a question there, Phil? Maybe not.
Better?
You're muted, Phil.
Oh, there you are.
Yeah,
Phil.
okay. Here I am. Yeah, urban settings where you've got property rights and you're changing the hydraulic gradient on private property and a number of things, and things are not on Forest Service land, etc. How has that gone?
Slow. I think I think most of what we've been doing is so if there's no work being done on a private property land, then we have to go through that. That's the FEMA process I was just talking about. We have to look at what changes has occurred. And it particularly happens on the downstream side, right? If you had a downstream landowner and there is a localized rise in the stream flows, but in the majority of cases, it comes to its equilibrium. It returns back to its water surface elevation that it was in existing conditions. It's a localized rise. It's just no different than upstream. In the existing condition, you have a backwater effect. You remove that constriction, that backwater locally goes away. But if you were to go chase it upstream in existing conditions, you would have the same water surface elevation in existing proposed. So most of the changes in this is that continuity of fluids, where the fluid's the same CFS coming from upstream is the same CFS downstream, whether in existing proposed conditions. It's just velocities and water surface are changing locally. So I don't know if I answered your question, other than we are looking at what we call on the washed out side, we're looking at what we call flood risk assessment memos. And so we're actually specifically answering that question for each site. And that's a requirement for every site, is to analyze the site to see what the risks are, and coming out with like, okay, it's the low risk, or this is a high risk. Where the additional elevation downstream is actually flooding into somebody's basement. That's a high risk. We need to address that. Is that acquisition? Is that what does that look like? But one thing that might be of note is the Attorney General has made a decision to say that as long as you're restoring natural conditions and natural processes, then the state cannot necessarily be liable for the future conditions. So it's kind of one of these things where we created constriction early on. Now we're restoring it in its natural processes, and now essentially the state's saying, hey, we got out of the way of this natural processes. Now whatever happens, happens. So I think that's a little more sticky than I just made it sound to be, but that's kind of going to be the general stance as these all start rolling out.
Okay. I mean, it's a huge topic, and I'm just wondering how you've fared so far with it. So.
Yeah, I think we fared fairly well. I mean, the modeling helps us support, right? There's the engineering. I kind of poo-pooed a lot of the engineering, but in the end, that's the piece that we can say, hey, we got the topo, we got developed a mesh, we got a model, we're running through the hydrology, we can anticipate the existing, we can anticipate the future, and so we, most cases, can identify what that risk is. And then once we identify the risk, we say, okay, how do we mitigate that? Or is that something we need to mitigate? And so we are looking at it, I think, from on a washed out side, project to project, but I don't know if other folks are looking at that.
Okay, thank you.
Yeah.
Awesome. Well, it looks like we have time for one more question, and Lisa's had her hand up. So Lisa, if you would like to ask your question, feel free.
Yeah, I was gonna some of what I was gonna say has already been answered through these last few, but I was gonna say, yeah, definitely don't discard the engineering, because I did a project down in Florida where we did a lot of critter crossings in a wetland, and the downstream neighbor had flooding on his property to begin with. And so as soon as we got the design done, he tried suing. And it was my calculations that kept the state and county from having to stop the project and look at more options. So, I was able to say, he's already flooding and we're not making the flooding any worse. He built in a wetland, which he never should have done, and the wetland is going to continue. So we as engineers are very important on these projects.
Thanks, Lisa. Yeah, I kind of understated it, but everyone's doing the right thing, and I forgot my group that I'm talking to, that is the piece of why we're there. Is like I said, the risk to infrastructure, life, and property, and so those are absolutely critical. And in the end, that's the engineers required. So thank you for sharing that.
All right. Let's see if we have any last minute questions. Lots of kudos to you, Gabe. Most people are saying
thank you. Appreciate it.
Henry, who says the best part is that your kids are following and checking your work.
Yeah, they are.
Sweet. Well, I guess that is all the time that we have for questions. So if you have any follow-up questions, feel free to reach out to the EWRI email, and we can follow that up with Gabe and get you some answers. So thank you so much, Gabe, for coming and taking the time to present to us. Super helpful, and it's a really interesting topic. So thank you so much.
Thanks, Caitlin. Thanks for having me. Appreciate it.
Yeah. Oh,
Thanks,
and then
Gabe.
in terms of EWRI, we're going to be taking a break in December, and so you can catch us with our next meeting in January. So happy holidays, and I hope you all have a wonderful end of the year.
Hey, if you guys are needing another meeting, check the chat, because we do have ASCE has other meetings in December since this group isn't going to meet.
Awesome. Thank you so much, Lisa. I will send out that information.
Thanks.
Thank you, everyone.
Right.